Now, yesterday I discussed about resistance and its limitations of resistance. Now, let us see what is resistivity. Resistivity. Resistivity rho. Resistivity rho. Now, we know Ohm's law. What is Ohm's law? Ohm's law is V is equals to IR. I told yesterday this is only a basic law. It is an empirical relation but not a universal law. Now, at a constant temperature, the resistance of a wire or a metal is directly proportional to the length of that wire. Directly proportional to length of that wire. This implies R1 by R2 is equals to L1 by L2. At a constant temperature, the resistance of a wire is directly proportional to the length of that wire. Therefore, R1 by R2 is equals to L1 by L2. This implies delta R by R is equals to delta L by L. In first chapter, errors and approximations, we can write this one as like this. Delta R by R is equals to delta L by L. And also R proportional to 1 by area. Here A is area of cross section, that is equals to, let us take it as pi r square. Area of cross section, that is pi r square. This implies R1 by R2 is equals to A2 by A1. R1 by R2 is equals to A2 by A1. Also, as here A proportional to R square, this implies R1 by R2 is equals to A2 by A1, that is equals to R2 square by R1 square. That is equals to R2 square by R1 square. This implies delta R by R is equals to delta A by A. If you want, you can take a negative sign because it is inversely proportional. Resistance increases, area decreases. Therefore, you can take a negative sign here. That is also equals to minus of 2 delta R by R. Minus of 2 delta R by R. Minus of 2 delta R by R. This is the useful in doing the problematic part. This is when this one and this one are useful in doing the problematic part. Delta R by R is equal to delta L by L, and delta R by R is equals to minus of delta A by A, and this is equals to, as A proportional to R square, R is the radius, then that is equals to minus of 2 into delta R by R. This is something like this. Now, what is resistivity? I have discussed R proportional to L and R proportional to 1 by A. R proportional to L and R proportional to 1 by A. A is area of cross section. This implies R proportional to L by A. R proportional to, combining these two, we get R proportional to 1 by A. ORR, R is equals to some constant rho into L by A. Some constant rho into L by A. Here rho is called as resistivity. Rho is called resistivity. Rho is called the electrical resistivity. Now, what are the units? Now, how can we define resistivity? Definition of resistivity. See, if A is equals to 1 square unit and L is equals to 1 unit, then R is equals to rho. Then we can define resistivity rho as, it is the resistance of a wire. It is the resistance of a wire of unit length having unit cross-sectional area. The resistivity is defined as the resistance of a wire of unit length having a unit cross-sectional area is called as resistivity. Now, what are the units of resistivity? Units of resistivity. Units. Here rho. Here rho is equals to, from this equation, rho is equals to RA by L. Rho is equals to RA by L. Now, resistance R is ohms. R is ohms. And area is meter square, length is meter. This simply is equals to ohm meter. Unit of resistivity is ohm meter. Unit of resistivity is ohm meter. Now the reciprocal of resistance, I have discussed this in the last class. Reciprocal of resistivity is called as conductivity, and I have given you units also there. Okay. Now I have to say 1 by NE mu in terms of mobility. I have discussed all this. NE square tau by m. All this discussed in the class 4. This is class 5. In class 4 we have discussed all these things. Now the reciprocal of resistivity 1 by rho is equals to sigma, the conductivity. You may remember, if you hear yesterday's class, sigma is called as conductivity and the reciprocal resistance is called as conductance. 1 by R is equals to G. This is conductance. This is 1 by rho is called as sigma. Conductivity. Conductance G. Conductivity is sigma. Okay. Now it's called conductivity. Whose units? What are the units now? Units are units of conductivity. Units of conductivity is sigma. It is useful in chemistry also for you. So sigma is equals to ohm inverse. Reciprocal of this one, no? Reciprocal of this one. Ohm inverse, meter inverse. Ohm inverse, meter inverse. But ohm is also called as mho meter inverse or mho per meter or mho per meter. I explained you in previous class also. Reciprocal of resistance is called as conductance, whose units are ohm inverse or Siemens. Siemens. I told you this is called as Siemens. Therefore, ohm inverse is called as Siemens. Therefore, Siemens per meter. Siemens per meter is also a unit of what do you call this? Conductivity. Okay. Now, what are on what factors resistivity depends? Resistivity does not depend on the dimensions of the resistivity. Does not depend on the dimensions of the particular material. Does not depend on the dimensions of the material, but it is independent of dimensions of the material. What will be the length? What will be the area of cross section? Resistivity does not depend on the dimensions of the material. R rho is equals to RA by L. Now, for a fuse wire, which is a tin lead alloy, for a fuse wire. I think you know fuse. We use fuse in this household, no? For a fuse wire, which is a tin lead alloy. Resistivity is very low and melting point is also very low. The resistivity and melting point for a fuse wire, that is a tin lead alloy, should be very low melting point, should have very low melting point and very low resistivity. A tin and lead alloy, which is a fuse wire, should have low melting point and low resistivity. Okay, so low resistivity means current is high. High current flows, heat will be generated is more. Then what happens? Then it will automatically breaks off. Therefore, our house is safe. Therefore, the fuse wire should have low melting point and low resistivity. And the heating elements. What are heating elements? We use heaters, no? Which is made up of nichrome wire. The heating elements, which are generally made up of nichrome wire, should have high resistivity and high melting point. They should have high resistivity and high melting point. Fuse wire should have low resistivity and low melting point. Heating elements should have high resistivity and high melting. They should not melt. High current passes through it. Therefore, it should have high melting point and should have high resistivity. It should be heated up. V square by R, we say that generally we say. Therefore, high resistivity and high melting point. And filament. In electrical we are having filaments, no? In filaments. For the filament, it should have low resistivity and low melting point. Low resistivity and high melting point. For a filament, we have high resistivity and low resistivity and high melting point. Filament means bulbs, no? Therefore, it should not, even though it gets heated up, it should not melt. Therefore, it should have high melting point and low resistivity. It should passes high current, and therefore, these are the three important phenomena. Very important one: Fuse wire, low resistivity, low melting point. Heating elements like our heating water heaters, they should have high melting point and high resistivity, and filament should have low resistivity and high melting point. Now, how the resistivity varies with, see, I told you that R is equals to rho L by A. We derived R is equals to rho L by A, and I told you R proportional to L and R proportional to 1 by A. These are correct if you consider two different conductors. But if you consider a single conductor, if you stretch it or compress it, what happens? If you stretch it, then what happens? Length increases, area of cross section decreases. These are for the different materials. Okay. Now, if you consider a single conductor, single wire, if you stretch that wire, what happens? The length of the wire increases, area of cross section decreases, but the volume remains constant. What is the volume of the wire? If you consider this as the wire, this is the area of cross section, this is length here. If you stretch it, then what happens? It may get like this. This is L dashed greater than L, and the area of cross section becomes very, very low. Area of cross section becomes very, very low. Area of A dash, what happens? A dash less than A dash. But what is the volume here? AL. Volume here. Area into length gives volume. What is the volume here? Volume V is equals to A dash L dash, but total volume remains constant. Therefore, A dash L dash is equals to AL there. Volume remains constant. Therefore, keeping that in mind, if a problem is given that if the wire is stretched or elongated, then what happens? So there R is equals to rho L by A. R is equals to rho into L by A into L by L. We can write this. R is equals to rho into L by A into L by A. This implies R is equals to rho L square by V. Area into length. Area into length is equals to volume V. Rho L square by V. Here V remains constant. I told you it is stretched, single wire is stretched. Therefore, R proportional to L square. If a single wire is stretched, then you have to use the formula R proportional to L square, implies R1 by R2 is equals to L1 square by L2 square. When you have to use the formula R proportional to L, this should be used when you consider the different wires. If you use the different wires, if you use the single wire and it gets stretched, then volume remains constant. Then we have to use R1 by R2 is equals to L1 square by L2 square. R also we can write. Therefore, R is equals to what we have? R is equals to rho L square by V. But we know that mass density is equals to density D is equals to mass by volume. Density D is equals to mass by volume, implies volume is equals to mass by density. Therefore, implies R is equals to rho L square by, in place of V we can write mass by density. R is equals to rho L square D by M. If two materials of same density and different masses and different lengths, then we can see two materials of different masses, different lengths having same density, then what happens? R is equal proportional to L square by M. We can use R proportional to L square by M depending on the conditions given in the problem. You can use this formula. R is equals to rho L square D by M. Similarly, R proportional to, this is one format. Similarly, if for this one R is equals to rho L by A, we have multiplied L by L. Now multiply with A by A. Then what happens? R is equals to rho L into A is volume V. Rho V by A square. Therefore, R proportional to 1 by A square, implies R1 by R2 is equals to A2 square by A1 square. R1 by R2 is equals to A2 square by A1 square. But again, A is equals to pi R square. This implies A square is equals to pi R power 4. Pi R power 4. Therefore, R proportional to 1 by R power 4. This implies R1 by R2 is equals to 1 by R1 power 4 by R2 power 4. R2 power 4 by R2 power 4 by R1 power 4. Therefore, R proportion 1 by R power 4. Here R is radius, this R is resistance. Therefore, R1 by R2 is equals to R2 power 4 by R1 power 4 and proportional to A2 by A2 square by A1 square. A2 square by A1 square. So these are all very useful in doing the problems and very useful in doing the problematic part. Now, here again, as here for this equation, from this equation again volume is equal to mass by density. Therefore, R is equals to rho into volume is mass by density, A square into D. R is equals to rho m by A square into D. So this is something the variations of resistance with length and its area of cross section and densities. And what is resistivity? The resistivity is independent of the dimensions of the material but depends on the meter. For copper it is some x, for aluminum it may gets various, but material to material it gets various, but for the same material it remains constant. If you take aluminium in India or America, for aluminium resistivity remains constant. So that is the thing here. Now let us see how the resistance varies with temperature in the lecture 6. Okay, thank you.